Good morning, mathematicians, and welcome to Office Hours. We're streaming live from the office. I hope you're all doing well. I hope you've all had a very productive Monday filled with proofs. If I could get my stream to pop up, there we go. I could get chat going. Hello, quality. Good morning. Looks like you're back on top, back in lead. We had a real mix-up, a real grab for power in the last couple days. Good morning, Lico. Had a lot of new faces to be first in chat. Okay, well, what is there to yap about today? So many things. I did not go read up on italomorphisms to write down some examples for you. Sorry. It's also been on the back of my mind to read up on do some Chern classes. I got very inspired by all the Chern class questions. It kind of made me feel like I wanted to do some Chern theory, but alas. These next couple days are gonna just be about research and the main sort of videos, that video series I'm working on. Good morning, Yaman. Is math a young man's game? Interesting debate. Here's the thing. Every time this question comes up on Reddit, there's always people who are like, oh, Weierstrass, didn't do anything until he was like 60 or something like this. And yeah, it's definitely possible to make important contributions later in life. But the truth is, like, most things are a young man's game. Maybe not... you can still do pretty good at long distance running into your like 40s and 50s, but like, yeah, pretty much everything is a young man's game. You know what I mean? Like, well, this is obviously wrong. Of course, original math can be done after 30. That's insane. And even like pretty important original math can be done after 30. But like, yeah, I think if you look at all the craziest stuff that's ever been like done or invented, of course, yeah, you come up with a million exceptions. Politics is the opposite. Yeah, is it though? I mean, like, is it necessarily true that you do your best? Like, it's just set up in such a way that only older people seem to gain positions of power in politics, because you need like so many years of experience. So, but what are the reasons for that? Like one, you could say, well, there's a lot to learn about the world in order to like have a higher up position in politics, and it simply is a matter of time to learn about all of these processes. But it could also just be like a sociological reason. So, yeah, I don't necessarily know. Yeah, I wouldn't say that it's necessarily true that people in politics are doing, like, it is an old man's game, but I don't think that's because you're like maybe better at being a politician, strictly speaking. It could be, but I think that's not so clear. Yeah, maybe at 60 you're probably not going to have so many original ideas. I don't know. I wonder what people think. Yeah, archaic views. Yeah, I mean, okay, again, people are going to come out of the woodwork with like a million examples, right? People are going to come out of the woodwork with a million examples, but this is not the typical experience, right? Andre Vey also had the rule for Bourbaki members to leave after 50. Oh, interesting. Yeah. Yeah. I mean, it does make sense. Yeah, I don't know. There's also like studies. This isn't quite the same as math, but there's studies suggesting that like after 30, people's music tastes, for example, are usually like pretty set in stone. And I like to think this isn't the case for me, both because my music tastes have sort of always been eclectic. Hello, Fimnal. Always been eclectic and growing, and ever since I heard the statistic, I'm also like, I feel even more like, okay, I need to really like, I want to keep an open mind. I want to continue to grow in that way. So, uh, yeah, but oh, yeah. Anywho, let's see what else is out there. And then we'll yap about maths. What's my favorite proof of fundamental theorem of algebra? Let's see. There's probably some cool ones here. I mean, I like the one using the fundamental group. So we're just using algebraic topology. You're surprised to hear? Oh, there's a Riemannian geometry proof. Interesting. Interesting. Yeah, I like the fundamental. Yeah, non-constant monic polynomial has a complex root. Yeah. How does this one go? Oh, this is also very homotopy theory. Yeah. Yeah. I mean, that's kind of the one that sort of generalizes. I was talking before about the fundamental theorem of algebra for octonians. The most elementary one, if a polynomial had no roots, its reciprocal would be an entire function. Ah, yeah, this one from complex analysis. Yeah. Yeah, that's a nice one. Regular value theorem. Let f be a non-constant polynomial, then it extends to a smooth function on the sphere. The critical points of f correspond to zeros of its derivative. So there are finitely many. This implies f has at least one non-trivial regular value. Fundamental theorem for octonians. Yes. Yeah. It's true. It's definitely true. Where do I have it? Let's see. Desktop, courses. Where did I put my courses? Nope, my courses are in my documents. Let's see. Rings and modules. Yeah, I have the paper in here somewhere. Let's see. Can I shrink this so that I can keep an eye on chat? Construction of octonionic polynomials. Is that it? Is this the paper? Give me a second. Yeah, here we go. I think I showed this paper on stream actually already. But oh no, this isn't the paper that proves it. This is just talking about defining octonionic polynomials. But rings and modules project. A note. Oh yeah, this is the paper. This is a paper. A note on the fundamental theorem of algebra for the octonians. So this is a proof that uses. We did talk about this a couple of weeks ago. I'll probably, as the channel gets more popular, I'm probably going to be repeating myself a lot more. but oh well, that's the way it goes. So here's a paper if you wanna go take a look. It uses some like basic topological K theory, and well, I don't know how basic it is. Well, I don't think it's the super deep topological K theory. And stuff about vector bundles. So yeah. I've been thinking about making some shorts, making a bunch of YouTube shorts to talk about all my favorite theorems and just have little mini proofs as shorts. I think that could be good, but we'll get there. Okay, tell me up about math. Please roll in your questions if you got them, but otherwise, what am I going to go back to? Oh, okay, so yesterday I introduced the idea of the Weil group. So the Weil group is, well, basically, so I told you that it, formally, we'll define it as the normalizer of the torus, modulo the torus, but then I gave you as an example for GLN, it just ends up being isomorphic to the symmetric group, where each of the elements of the symmetric group is represented by the corresponding permutation matrix. Do I know about Peter Schultz's condensed mathematics? I know of it, but I don't know about it. Yeah, I know very vaguely that the idea is, we're sad that topological groups aren't in abelian category, and so we try and come up with a new abelian category that should somehow capture topological groups. Hello, astromathics. And yeah, that's basically the idea, and that's how we get to condensed abelian groups. But that's about all I know, is just this tagline understanding of it. Yeah, that's the extent of my knowledge on condensed mathematics. Another thing that would be nice to learn, but there's never enough hours in the day. Video title idea, yeah. I appreciate it, Lika. It might happen. Hello, Nicole. Yeah. So one other thing I wanna talk about is so we have the notion of characters, which are basically one-dimensional representations of group. So if we have a torus, in particular, we could have a character. You're done with Jordan Algebra's problem set. Woohoo! You did 20 out of 23, and that's it. Wow, 23 problems. That's a big problem set. Yeah, in my analysis 3 course, in Ph.D. Yeah, you did. The professor will read it. Yeah, so in my analysis 3 course, ultimately the homework portion of it was to do 40 out of 50 problems between baby, Papa, and Grandpa Rudin, and there was sort of sets of 10 were released periodically. Yeah, and I don't think he read a single one, because there was definitely, I'll be honest, there were some questions towards the end that I just like half-assed, because they were difficult, and it's a lot of questions, and I got an A+, and I know for a fact that some of my proofs weren't correct, but yeah. Which, I don't know, maybe that's not the worst thing, right? You just sort of like tell students that they have to do something impossible, and seeing how far they get. Good morning, Sarks. Like, I actually like the idea of like giving students an impossible exam that's just like it's too much to do in 3 hours, but just really like see how far they get, like really let them push themselves. and then afterwards like curve the grade or something. I like that idea actually. Yeah, fair enough. But I mean, you're so much stronger for it now. You know so much more about Jordan algebras. Good morning, Adib. Good morning, Adib. So we've got characters. We've got some characters of the torus. We also have so characters. So, but in this case, this time I'm going to talk about p-adic characters of the torus. But we also have something that, so because I'm thinking about this torus over a p-adic field. We also have maps going the other way, though, and these are called co-characters. Co-characters. So it turns out that, by the way, each of these characters, so for each integer, we have a character that sends t to t to the a. And going the other way for each co-character, oh, sorry, I wrote f, but I meant t. For each co-character, we have a map that sends x to, well, actually, it will be, well, I lied about a little bit. This isn't just, sorry, this doesn't make sense. Let me correct my mistake here. Each character, if this torus is rank n, then each character will be given by an n tuple of integers, which sends t to t1 a1 times t2 a2 up to tn an. Is it an inverse co-characters equals characters? Not exactly, but there is a well, you'll see in a second. There isn't really, in this case you can't just put the prefix co, like you often can. Do you have Mackey's theorem to p-adic groups? Well, Mackey's about the decomposability, right? That's the one that's about the fact that your representations are direct sums. And in that case, no, absolutely not. So I think in previous office hours, I talked about how there's this, from GL2, there's this induced, we take these characters, we take the p-adic norm characters on the torus and induce it. And this representation has the trivial representation as a sub-representation, and then it had an infinite irreducible representation called the Steinberg representation as its quotient. And this is not split. So you cannot write this as a direct sum. And so in some sense, the representation theory is therefore much more interesting because now we have non-trivial extensions. I do not have any sources for learning about cobordism, unfortunately. I've never learned about it. I mean, looked at like the wiki page late at night at some point, but I've never learned about it. So meanwhile, right, so we have our characters of the torus, but we also have co-characters. So those are just maps that go in the opposite direction. And it's a very similar story. It's a very similar story to the characters, and that is we send an x to the diagonal matrix. So again, we have one of these for each tuple of integers. Each tuple of integers, where this is x a1 ... x a(n). And so what we do get though is if we compose these, if you compose these maps, it turns out that there's always so if you apply, gosh, I don't know, call this a character, call this a co-character. So if you apply this character to the application of the co-character to x, it will always be x to some integer. And so we call this, maybe we tend to write it on the other side, whatever. But if we write it like this will always be an integer. And this actually defines what we call a perfect pairing between x lower star t, so this is the set of co-characters. This is the set of characters here. And this map sending these to that integer is a perfect pairing. So basically what that means is we get isomorphisms. The sort of abelian group HOMs are isomorphic. So characters and co-characters are dual to each other in this sense. So read a bit about Frobenius algebras and topological quantum field theory. Oh, interesting. My torus is split. Yes. I'm avoiding all of this terminology, split and non-split. Maybe we'll get into that eventually. But yeah, I'm assuming everything here is like the nicest case possible. Oh yeah, I love beach math books. I love beach math books. There's not enough beaches near where I live right now. Actually, that's not true. I mean, there's some, but it's okay because I've got mountains. Am I following some syllabus for my series of live streams? No, everything is just off the top of my head. It's literally random what I talk about every day. Well, I mean, some things are going in order as I'm talking about my research, but everything's like completely off the top of my head. I mean, stuff about characters and co-characters you'll find in any book about algebraic groups. Like there's Springer's linear algebraic groups. That's a good one. I guess Humphrey's book on algebraic groups. Also, if you're more interested in heading towards like the Langlands type stuff, some of this stuff is covered, though it's more like a brief review in like Getz and Hahn. So Getz and Hahn, Humphreys, Springer. Yeah. But it's all off the dome. It's all off the dome on these live streams. I'm mostly just yapping until someone has questions for me, unless I get carried away in what I'm yapping about and then ignore the questions. You live right next to a beach, incidentally. Nice. Just came back from a long walk next to the ocean. Wow, that sounds fantastic. I'm happy for you. Sounds like a good setup. So we've talked about the vowel group. We've talked about co-characters. And so now I can freestyle math. That's the next level, is to start having rap battles with other mathematicians where we're freestyling like proofs and dissing each other. I feel like we need to bring back that energy. You know, the energy of Italy in like the 1500s. They used to have like public math battles. You know, we need to bring that energy back. Okay, so there's a reason why I was talking about vowel groups and co-characters. In the back of my mind, I am trying to get back to description. There's a special algebra that we talked about before called the Iwahori-Hecke algebra. And we're interested in this because it actually captures an important class of representations of our p-adic groups. And so At the moment, we just have a description of this as some, algebra of functions with some nice properties, but it would be nice to have explicit generators and relations. And so now we do have there's an explicit set of generators and relations here. So first, I'm going to describe a basis of functions for this algebra. What is this basis given by? Well, first off, for each element in the Weil group, which I guess we can take as take it in terms of this normalizer. So technically, W is an equivalence class. But pick any representative you want. It's going to turn out that this definition is free of the choice of representative. We're going to take the characteristic function of so this is the Iwahori subgroup. We'll put some Weil group element in the middle, and so we have this like double coset. So I'm going to find T tilde W to be this function. And it turns out you can prove, actually, and I think I mentioned this before as we were striving towards, this is the part that corresponds to the finite Hecke algebra. So it turns out that so I guess there's a fact I should remind you of in order to say this. Maybe I'll talk about that after. I'll just say the functions. So yeah, IWI, yeah. And then there's one other function. So, oh gosh, actually I need to say some more words to to describe the other thing. Yes, like a vector space basis, exactly. Like a vector space basis. That's exactly what this is. Actually, wait a second. What I'm about to tell you might give you slightly too many things to be a basis, but at least these elements generate the algebra. At least these elements that I'm about to tell you. I'm explaining what the Iwahori-Hecke algebra is now. I mean, its definition. If you go back, look at some recent live streams. It's smooth, meaning locally constant functions from your p-adic group into the complex numbers, which is bi-invariant. So if you multiply on the left or the right by something where these ki's are in the Iwahori subgroup, it does nothing. But okay, you can look at recent live streams for those definitions. The other class of functions, gosh, okay. What's a way to describe this? So it turns out that there's a notion, I'll just tell you. It turns out there's a notion of dominant co-character. So there's a general definition, but I'll just tell you as an example in GLN, although actually I think some people take the opposite convention I'm about to, so that's another source of confusion for writing things properly in my thesis. But right, so a co-character is going to be given by sending x to this diagonal matrix determined by some integers, and if it's dominant, we might say it turns out that in the case of GLN, being dominant is equivalent to this condition. Yes, it is exactly like what you wrote in chat. Yeah. In fact, like another notation we use is this, where K is the Iwahori subgroup. Yeah, exactly. So now what we're gonna do, and it turns out it turns out that for every co-character, there exists a pair of dominant co-characters. such that mu is mu1 minus mu2. So, even here's a challenge to chat. I think even if you don't understand most of the words that I'm saying, you might be able to at least prove this, say in the case for GL2, just prove it by hand, using my fake definition of dominant co-character. So I challenge you to do that. And so now I'm going to define one other function for each co-character. I'm going to define another function. Well, first I'll define for the dominant co-character. I'm going to define this to be the characteristic function of I. What am I going to put in here? I mu1 of. So I'll say what var pi is in a second, but of a particular element. So this is called the I don't remember, the uniformizer. In the case of it's basically, the thing is like we have our p-adic integers, and p generates the maximal ideal in the p-adic integers, and then, but more generally, like if you take some extension, then we also have a ring of integers, and it also has a unique maximal ideal, and you can also take some whatever generator you want of that. Hello, Dead Star. Good morning, Dead Star. So, I promise this will be slightly less abstract in a second. Actually, I don't know, I shouldn't promise that, but it might be. So now I'm going to define a function t tilde mu, which is going to be, gosh, as I keep defining this, there's like more and more things that I'm like, oh, actually there's, I'll explain this later. This is some character. It's some character we have to normalize by. It'll be this, where this star is the convolution operator. Okay, but it turns out that these, so whatever these things are, these are some crazy definitions I've given you. I'm sorry, but this Iwahori-Hecke algebra is generated by t tilde w and t tilde mu, and in fact, this is what allows us to give. So I talked about how this, yes, Yamin's right. It is the modular quasi character. But I haven't defined that yet. So I'll explain more in a little bit, what that is exactly. But the point is that we sort of can now, get, like a morphism with, there's this thing called like the Iwahori-Hecke algebra of type AN, which is given just in terms of an abstract presentation of generators and relations. And that definition is given as such. So we also have a TW. I'm going to write it without the tilde because we're not thinking of it as a function. And T, again, labeled by co-characters. And in this case, the relation, so one of them I talked about before is if we have, I'll say what TS is in a second. It's a special element of the Weyl group. This is Q, or you can think of it as just P if it's our p-adic field. This is, the way I've written it here is actually an infinite generating set. However, you only need finitely many things, because so your Weyl group is going to be finite, so you have finitely many terms coming from here. These will be, these functions will be, you have infinitely many things in your, like, infinitely many co-characters, but of course your co-characters have some sort of like basis, some sort of finite generating set themselves. And so if you just write down that finite generating set and the rest of the relations, you can actually give this algebra a finite presentation. You can actually give this algebra a finite presentation, yeah. So we have this relation. So I'm going to need to do a little bit of work to explain the two statements that I'm writing down here, which I'll do in a second. But we have an abstract set of generators and relations. So these are relations on the T corresponding to Weyl group elements. And then I might actually just pull up the actually wait. Here we go. I might just pull up the relations from this paper instead of writing it out. I'd rather not get it wrong. I'd come within an epsilon of the truth, but why not? Why not be even closer to the truth? Here's the relation. So this is the one other relation that we need here. The theta that's written here, that's just the t sub mu. So they just use a different notation, theta sub mu, but that's the same thing as the t sub mu. In a moment, unless I get distracted by other viewer questions, in a moment I will, we'll look at the case of GL2, and we'll write this down explicitly in the case of GL2. So we have that extra relation. Oh, and we have the fact that T mu times T lambda is T mu plus lambda also. Okay, so what is this S here? Well, remember in the case of GLN, our Weyl group is the symmetric group on n elements. And the symmetric group has a special set of generators. So it is generated by just what are called the simple reflections. So that's the reflection. So just the permutation that just swaps 1 and 2, the permutation that just swaps 2 and 3, ... up until the permutation that just swaps n minus 1 and n. And it turns out that there's an analog of this for every Weyl group. So it turns out those also have just a set of so-called simple reflections. And so that's exactly when this quadratic relation holds, is when it's one of these simple reflections. The other condition here, this L corresponds to the length. So what is the length of something in the Weyl group? Well, just like so let's say our Weyl group is generated by n things. I mean, in this case, it's n minus 1 things. But let's say our Weyl group is generated by n things. Then that means that everything in our Weyl group, maybe I'll write it as a W. Everything in our Weyl group can be expressed as some word in these generators, right? And now this word might be reducible because we might have some extra relations, but the length of W is defined to just be the length of the minimal word describing it. So there might be more than one. There could be two different minimal words that describe it, but their length, I mean, this is some theorem you have to prove, but the length will be invariant. Yeah. I don't know if chat is loving this or digging this or what. But this is what happens when people don't ask questions. I'm just gonna rant about my own crazy nonsense. So, okay. Let's look at an example. W is like a free monoid. Well, W isn't. W is No. No, not exactly. I mean, W, well, you've written lowercase w there. Lowercase w is an element of the vowel group, and the vowel group is a finite group, right? It's just like, it's like the symmetric group. It's like the symmetric group on n elements. So let's take a look. For example, let's take a detailed view at the affine-Hecke algebra for GL2 over a p-adic field, just the p-adic field. So let's take a look. Actually, before this, we have an even easier one, right? So like a split torus over say the p-adic numbers, of rank n. This is just going to be n copies of the multiplicative group of p-adic numbers. This thing doesn't have a vowel group. Vowel group is trivial. The vowel group of the torus is trivial, so we don't have any generators coming from that. Let's look at then our characters. It helps to remember the vowel group is the group of reflections of a root system. Yes, exactly, that's true. Just saw that the generating words you wrote before seemed very free monoidish. Yes, I mean, yeah. Has the vibes. I agree with you there. Has what I wrote has those vibes. Yeah. So what do we have? So our entire algebra is just generated by these things, just generated by these symbols as W ranges over the co-characters. But the co-characters here, right? So I said that each co-character is of this form. It sends x to the diagonal matrix, x to the a1 ... x to the an. So this means if I define mu I to be the co-character that sends x to just, so I'm going to choose all of these to be 0 except for one of them, so it'll just be 1 ... x in the ith position, and then everything else is a 1. Well, then you can see that all of my co-characters, like this essentially forms like a basis, like a z basis for my co-characters, right? As like a z module. So every co-character can just be expanded in additive notation in this form, right? But then that means that every one of these symbols, according to the rules that I gave above, basically just boil down to each of these rather a product of these things. And I guess the A's come out front for some reason. I don't remember exactly why we can make them come out front, but they do. What's a class? You've seen people saying it's too big to be a set, but that's like saying an elephant is too big to be an ant. It doesn't really explain what an elephant is. What can I read? Okay, let me get to that in 1 second. I'm just gonna wrap up one thought here, and then I'll jump to that question. So, set theorists out. Hey, be nice. Be nice. We're a very accepting, very accepting of all kinds of mathematicians here. Except people who believe in law of excluded middle. I said it. There we go. I said it. I use it daily. I use it daily in my work. So, settle down. But what does this mean? Well, basically, we can identify each one of these. I mean, all these generators and relations together essentially tell us that this is basically just a polynomial ring in n variables. So after all of these complicated definitions and everything, if we take the Iwahori-Hecke algebra of a torus, it literally just becomes it's literally just this but they're invertible. So it's a polynomial ring in x1 to xn, but we also allow inverses. That's it, right? So after all of this fancy stuff, but that's the point, right? So like I had to say all of these fancy words over several live streams to talk about these algebras that capture representations of p-adic groups. But the sort of the advantage of the, like this is the fact that it ends up just being the simple thing at the end of the day is kind of, it's like why this matters, right? Because it's like now if we want, we can study a very like important class of representations of say the p-adic torus by instead studying modules over this algebra, and like this is something that's a lot more well understood. I will even tolerate physicists sometimes. Accurate. Okay, so what makes something too big to be a set? Well, basically it's the idea of like Russell's paradox, right? I don't know if I spelled his name right. Just not putting enough respect on anyone's name. So Russell's paradox, right? This basically says that, well, right? It's the paradox that if you create a set of all sets that don't contain themselves, then you get this contradictory statement that x is in here if and only if x is not in here. So you get an inconsistent theory. So then we came up with the axiom schema of comprehension. I will do the GL2 example afterwards. I will do the GL2 example afterwards. Or if I don't get to it because there's other questions in chat, possibly tomorrow. But I will do it soon. So the, what did I say? Complex comprehension. So the axiom schema of comprehension, I mean, basically you can go Google this, you can look it up, but it's just some schema that basically says that avoids that, it doesn't allow us to make these sort of constructions, therefore ruining our whole theory. And the idea is that somehow you can't just freely quantify over variables. They should somehow always belong to some other thing, right? So the problem is, so once we get to you know, we want to talk about like categories or something. So for example, say we want to talk about the collection of all groups, right? Collection of all groups. And definitely in the modern perspective in mathematics, we want to do this because we've got like functors, which are going between different categories, and this lets us like relate different branches of mathematics together. So if we look at the collection of all groups, well, it turns out that actually this is too big. What does it mean that this is too big to be a set? What I mean is there's at least as many groups as sets, right? So that is, if I wanted to have a collection, a set of all groups, I couldn't, because if a set of all groups existed, if a set of all groups exists, then so does a set of all sets, right? So that's kind of a problem, right? Because I mean, like if a group is just, it's a set together with some sort of binary operation. So of course, if you just forget that you had a binary operation, then you have a group, right? Or you just have a set. So there's at least as many groups as there are sets, but in fact there's more. In some sense, how do we even quantify more? We can't quantify more because we've gone beyond set theory now, technically. So so that's what people mean when something's too big to be a set. So like another example, of course, is the collection of all sets themselves. That is too big to be a set. What that means precisely is that we cannot create a set that contains all sets. Likewise, we cannot create a set that contains all topological spaces. So again, by saying that there's no set containing all topological spaces, that's what we mean by too big to be a set. Now, everything I just said has a very big asterisk, though. Very big asterisk. Depends on what you mean by a set. So everything I said here, I'm assuming is just an ordinary ZFC set, like a set as according to the rules of ZFC set theory. But I actually have a video on my channel where I talk about large cardinal axioms, which people, and I now agree with doing this, tack on extra assumptions called large cardinals, which means you suppose the existence of larger sets than ZFC can typically produce, and then you can actually say that the collection of all topological spaces forms a set, but it's at some sort of higher level. It's not a set of all sets. There's some way of stratifying it. Okay, I don't go the slowest in the video, but maybe I'd point you to that video to consult it for more details. But I hope that gives you at least a basic idea of what people mean when they say something's too big to be a set. So you have other options. You have options. So you could invent classes and then say, well, it doesn't form a set, but it forms a class. But I think, in my opinion, large cardinals, way better approach, because either way you have to go beyond ZFC. Why would you introduce a whole new name and a whole new object when you could just introduce a new axiom, and so everything is at least still a set? You know what I mean? Cardinals don't just define a set, they also vote on the next pope. Indeed. Yeah. May you suggest a different way to approach Hecke algebras? It's more of a physics perspective, and we love the easy way. Yeah, maybe I should. Maybe I should do it from a ground-up example-based one. I mean, maybe if I was teaching a course on it, that's what I'd do. But I'm just yapping. I'm just yapping to fill the void. So, in my very particular subfield, do I know in name all current contributors? Probably not, but I could probably list a lot of people off the top of my head, which I did the other day in stream. Someone asked me this. Was it you? Say how many people in the world can you comfy read or familiar or very familiar your paper? How many people are familiar with my paper? I don't know. Probably not a lot, but I've received comments on it. So, do standard set theory books discuss classes? No, not typically. But my favorite set theory book, well, the one I learned from is Herbachik and Hecke. And they do talk about large cardinal axioms, which are superior to classes anyway. So ignore classes. Just ignore classes. When people talk about classes, just pretend they're assuming the existence of a large cardinal. So you should go read about large cardinals and then just ignore people who talk about classes. That's what I say. We think of them as deformations of a vowel algebra. Yeah, that's true, but I don't understand. I don't know that approach as much. Well, yeah, sort of. But if you're familiar with deformations of ordinary groups, which I'm not, then for instance, you can at least see where they come from. Yeah, I mean, there's actually a lot of. I find Hecke algebras. There's a lot of different ways to see where they come from. I have not given you the easiest introduction to them by any means. I'm not claiming that at all. Yeah, there's also ways to build them out of like braid group stuff and other things. Yeah, I don't know. They surprised that normal people read Hecke. Have you met a normal person that reads Hecke? Do you think I'm a normal person? P equals infinity is the best prime. Debatable. Okay. Do we have time to talk about GL2? Maybe I'll yap a little bit about GL2 before we go. Mm. Professor of yours recommended that. Yeah, well, I mean, I don't work with set theory at all, really, either. It's just sort of for interest in cultural development sake. And so when I do run into things that involve large cardinals, which I do in my work, I can, be assured that I'm, understand something about what's going on. So let's go down. So let's talk about GL2. GL2QP. Its Weyl group is the symmetric group on two elements, which is just Z mod 2. Those matrices are given by, of course, the identity matrix and this permutation matrix. So we'll call that E. We'll call this S. Wait, is TE? I don't think. Yeah, so TE doesn't. TE is just going to be our. This is just our identity. This is just our one in our algebra. So we just have, and so there's no other like. Sorry, there's no other like interesting elements in our Weyl group. So we just have this one quadratic relation on TS, and that's it. And like if you multiply it out, you get TS squared plus 1 minus QT plus 1 minus Q. So that tells you how to multiply, right? You can move everything over to one side of the equation that tells you how to multiply TS by itself. But then you can also factor things out this way. So this would be TS. That should be S. TS. What am I doing? Yeah, TS plus 1 minus Q equal to Q minus 1. And so this basically tells you that what TS inverse is, right? TS inverse is going to be 1 over Q minus 1 times TS plus 1 minus Q. Since we're yapping now, you want to say a bit. Your general perspective on things in general is that they are computable. If not, then I'm not sure what the real world relevance could be. Things like classes. Yeah, I don't know what the real world relevance of classes or large cardinal axioms are. But they make certain kinds of math possible, or at least more tractable to do. So I don't know. It just makes the formalism nicer. Like you could use sheaves to solve differential equations, and differential equations are very real world. But if you want to talk about the category of sheaves on like a topological space, even a very like just the real numbers, like that's already too big to be a set. So now you need a large cardinal to just. I mean, there's ways you can do it without assuming the existence of a large cardinal, but it's just really nasty. But then there's also things are more on earth and in heaven that have been dreamt of in your philosophy. I try to keep that in mind too, yeah. Have I read on forcing? You always forget how those detailed arguments on construction model of ZFC work. No, I haven't really read on forcing, but eventually in my sheaf series, Who Gives a Sheaf Theory series, I would like to cover topos theory eventually. And it would be great to discuss in sheaves in geometry and logic. They discuss forcing from the perspective of topoi or toposes or topis. So I'd really like to understand that. Okay, let's finish off the Hecke algebra for GL2. The affine Hecke algebra for GL2, and then I'll go. Okay, so we've got our unit. We've got this one generator that we understand. What are the other two? Well, I just need to understand this mu1 and this mu2, right? Those are my only other two things that I need to understand, basically. So then I just also have t mu1 and t mu2. And do I want to write this out? I mean, basically, all we just need to, like, the only other thing that we have is just this relation. I guess I should explain how the Val group acts, how the Val group acts on these things. So the only in order to understand the Hecke algebra, I mean, this is the one other relation, and the only thing I haven't explained is how the Val group acts. So I'll just tell you in this case that W of mu1 is equal to mu2. Or sorry, S. We have this one non-trivial element. S of mu1 is equal to mu2. And so that's basically it. That's basically it. So maybe in the future I'll tell you how to do some concrete computations with these things. And like there's stuff I prove in my thesis. Not, it's like small trivial details, but they're like things that you want to know. What is this paper called? This is called... Yeah, normally I give papers their proper name, but I didn't this time. On Bernstein's presentation of Iwahori-Hecke algebras and representations of split reductive groups over non-Archimedean local fields by Prasad. Yeah. So I think that'll do it for today. It's time to go prove some theorems. So get on it. Write some proofs. Ask some questions. Have fun.